Yeah, warm welcome to all. I am Gurumurthy, Assistant Professor in Department of Electronics and Communication from R.M.K College of Engineering and Technology. So this here we are going to see a short introduction about MOSFET circuits and how to solve problems in MOSFET circuits. So before that, we will have a short introduction about electronic circuit. Electronic circuit is a combination of both active and passive devices, where your passive device is going to control your active device, as well as there will be a signal path from input to output. So this is the path where the signal is going to flow through this path and it is going to go out of this amplifier. So if you take this circuit, it is called as an amplifier, where this transistor is nothing but the active device, and these two resistors are nothing but these two resistor R1, R2, RD, RS, all are nothing but the passive devices which is going to control this active device. So there is a parameter called small signal gain, which is nothing but minus RD into RS. So this minus RD, in this case, it is equal to 7K divided by 0.5K, which is nearly equal to 14 times. So the input magnitude as well as the output magnitude are going to differ by 14 times. And this minus says there is a inversion between input and output. So a circuit, electronic circuit, will normally consist of both active and passive components arranged so that the passive components control the action of the active components and act as a path for signal waveform. So what is amplifier then? It magnifies the input signal and produces output signal whose magnitude is larger and directly proportional to the input. So this is the box which is going to have amplifier. I do not know what is there inside this amplifier circuit. So it should have DC voltage and AC voltage. So now you can design amplifier or any electronic circuit will contain both active and passive. So we are going to use active and passive devices. So inside this box we are going to have active. In this case we are going to deal with MOSFETs, and passive we are going to use resistors. So in the previous case the gain was equal to minus 14. So this is the input signal, and the output is going to have, it is gain is minus, so it says it is out of phase. So this could be achieved only when, so the input and output is linear, but the transistor which is going to be present inside this amplifier is going to be non-linear. We should make this non-linear device into a linear device by doing what is called as biasing. So biasing, in the case of biasing, when you take MOSFETs, output characteristics, the device can operate in triode region or in saturation region. So I want to make my drain current as stable as possible. So as stable as possible, it should not vary. If that is the case, I should bias the transistor in this region. So it says that my VDS should be greater or equal to VGS minus VTH. So this is the boundary. So below this, when VDS is smaller, so VDS is going to be smaller than VGS minus VTH, the device is going to operate in region which is called linear region. So it is going to act as a normal resistor, where when I increase the voltage, my current is going to increase proportionately. So this is the condition for saturation. So for faithful reproduction, I should fix the amplifier in saturation region. My drain current will be Kn VGS minus VTN the whole square. This square term identifies MOSFET as a non-linear device, and we are going for biasing to act as a linear circuit, right? Then if you take a MOSFET, this is drain, this is source, this is gate. So this voltage between gate and source is going to control my ID. So if you take a drain current equation, it is mu n Cox by 2 W by L VGS minus VTN the whole square. I could write shortly as ID is equal to Kn, conduction parameter. So all these could be written as Kn into VGS minus VTN the whole square. So it says that this is Kn and VTN both are being constant. It will be decided by the technology people who are fabricating this device. So the only option to change or increase the value of ID or decrease the value of ID is with VGS. So ID depends upon VGS. So if that is the case, uh, if you know that any semiconductor device is sensitive to temperature. When temperature increases, my ID will increase. But in the case of MOSFET, we will see the condition what is going to happen to the ID. So when ID increases, my VTN is going to decrease. So when VTN decreases, VGS minus VTN, the whole term is to be squared, that is going to increase. So in the same time, my conduction parameter mu n Cox is going to decrease and ID will be constant. So a sort of negative feedback is provided by device itself. So ID will remain constant even if temperature changes. That is the benefit of using MOSFET in the analog circuits. So when temperature increases, your threshold voltage. What is threshold voltage then? So threshold voltage is the minimum voltage that should be applied to the gate terminal to create channel between source and drain. So this voltage will decrease when temperature is going to increase. If this is going to decrease, my VGS minus VTN, the quantity is going to increase. If that is increased, at the same time the conduction parameter is also going to decrease and it is going to make ID as constant as possible. So there is no compensation required for MOSFET amplifiers. So no stability issues. And next is, if you take any amplifier, it contains both DC for biasing and AC is meant for you are going to amplify the signal. So it involves both the AC and DC signal. You can, and the circuit is going to be linear. Then it says that you can apply superposition theorem to derive the terminal voltage and current characteristics. So superposition theorem can be applied. It states that if the circuit contains two sources, one is DC and the other is AC, at a time a source will be acting. If it is DC source, AC source should be made equal to 0. That case, the capacitor is considered as open circuit and the circuit is called DC equivalent circuit, where you are going to derive two important things. One is called as IDQ and another parameter which is called VDSQ, and these two parameters are called as large signal parameters. And then we are going to do AC analysis where capacitor is going to be considered as short circuit. Why? Because if you take this 1 by 2 pi FC reactance of the capacitor, when F is increasing, XC is decreasing. So I am going to consider capacitor as a short circuit when I do the AC analysis, but in the case of DC analysis, the circuit will contain purely DC, frequency will be 0, the reactance of the capacitor will be 0, so Xc is 1 by 0, so the frequency is 0 in the case of DC, so 1 by 2 pi f is 0, so 1 by 0 gets you infinity, reactance of the capacitor will be infinity, so the capacitor is considered as open circuit. So after this, when you do AC analysis, capacitor should be considered as short circuit, and then you will have to replace the transistor by its equivalent, which is called as a model, and we are going to use this model to replace the MOSFET transistor. What is a model? Model is a combination of circuit element properly chosen that is going to best approximate the actual behavior of the transistor operating in which region. I want to operate transistor in saturation region. You have two important things, GM and R0, which are called as small signal parameters. GM is dID by dVGS. So you know the ID equation, Kn VGS minus VTN the whole square. You differentiate the ID equation with respect to VGS, you will end up with this equation 2Kn VGS minus VTN the whole square. You can also represent GM in other forms, 2 into root of Kn ID, and GM could be written in other form 2 into ID by VGS minus VTN, and R0 is output resistance of the MOSFET, which is 1 by lambda ID. Lambda is called as a channel length parameter. ID is nothing but the bias current at the drain terminal. So with this introduction, we will go into the problem. Determine the small signal voltage gain and input and output resistances. So R1 is nothing but 70.9K. R2 is nothing but 29.1K, and RD is 5K. And VDD is 10 volts. So this is the given condition. So we want to find small signal parameter. Before that, we want to find or do DC analysis for obtaining IDQ and VDSQ. So to find ID depends upon VGS. So we should find VGS first. VGS is VG minus VS. It says gate potential is larger than source potential, and we know that source has already been at ground, so I can make this as 0. So VG is the potential at the gate terminal, which is nothing but voltage divider network, which is going to decide the gate terminal potential, into VDD. So it is 29.1K divided by 70.9K plus 29.1K into 10 volts. So I will end up getting 2.91 volts. So this VGS is going to fix my ID, which is going to operate with particular ID. So I could write this as VGSQ. So IDQ is nothing but Kn into VGSQ minus threshold voltage of the N MOSFET. So Kn, it is 0.5 into 10 power minus 3, 2.91 minus 1.5 volts whole square, which is nothing but I will end up getting 1 milliampere. So IDQ is 1 milliampere. Now I have to find VDSQ, right? So we have not considered the effect of capacitor, because capacitor is considered as open in DC. So this, when it is open, this part of the circuit will not have any effect on the circuit. So the remaining part is only this part will be there, which is nothing but the DC equivalent circuit. right? So next is we want to find VDSQ. VDSQ. So we will draw the circuit again. So this is 5K, this is 10 volts. I want this, and this is 1 milliampere. So VDS is nothing but across drain source terminal is decided by VDD minus ID into RD. So ID in the sense it is IDQ. So VDD is 10 volts minus IDQ is 1 milliampere. RD is 5K. So 10 minus 5, 5 volts. VDSQ is 5 volts. So we will check for the condition whether it is staying in saturation. So VDS is greater or equal to VGS minus VTN the whole square. Sorry, square will not come. So VDS is 5 and VGS is 2.91 minus 1.5. So 2.91 minus 1.5, it is 5 greater or equal to 1.41. So it says that 5 is always greater than 1.41. So MOSFET is staying in saturation. So DC analysis has been over. Next we will move to the AC analysis. AC analysis, where your capacitor is considered as short circuit. So if you draw the AC equivalent circuit, it will have RSI, R2. So DC sources should be made equal to 0. So R1. So RD. So this is my DC AC equivalent circuit. It contains only AC. So replace this MOSFET with model which is working in saturation region. So this will become, so RSI. If you take R1 and R2, the R2 other end has been grounded and R1 other end has been grounded. Both ends of, if you take two ends, if the first end has been connected, both R1 and R2 being connected here, the other ends have been grounded. So I could consider this as R1 parallel R2. So there is an open circuit at the gate source junction, and then I have GM VGS, and then I have R0, and then I have what is called as RD, and I am going to take the output here. So GM, I do not know what is the value of GM. So GM is 2 into Kn VGSQ minus VTN. So 2 into Kn value is 0.5 into 10 power minus 3, 2.91 minus 1.5. So GM, when I calculate this, I will end up getting 1.41 milliampere per volts, right? And if I look at the circuit from the gate source junction, I am going to calculate the input resistance. When I see the circuit, I have R1 parallel R2. So R1 is 70, R1 is 70.9K parallel with 29.1K. So the effective resistance will be smaller than 29.1K. If I do calculate it, I will get 20.6 kilo ohms. And if I look at the circuit from the output side, if I calculate output impedance, I should make input side equal to 0. If input is made equal to 0, VGS will become 0. GM VGS will become equal to 0, current source. So I will end up getting circuit R0 parallel RD. So R0 is nothing but lambda times IDQ. So lambda is, the value of lambda is 0.01 into ID value is 1 milliampere. So if I substitute this and calculate R0, it is R0 is 100 kilo, right? Sorry, it is 100 kilo ohm. So I want to calculate capital R0. So GM. So we will complete this. R0 is R0 parallel RD. So 100K in parallel with 5K. So if I do calculate this, 100K parallel with 5K divided by 105K I will have a value of resistor which is smaller than 5K, which is 4.76 kilo ohm. So already I have calculated Ri, which is R1 parallel R2, which is again 20.6 kilo ohm, and we have calculated GM. GM is 1.41 milliamps per volts. So we want to calculate gain, small signal voltage gain. So AV is my GM VGS is the current which is flowing through this output. So this end is going to be plus and this end is going to be minus. So current which is touching the first end of the resistor is going to be plus, and negative for the other end. It is called passive sign convention. This has been followed. So GM, and we are going to take at the negative end, so minus GM into VGS. We have two resistors in parallel, so put the two resistors. So VGS is across this. So RSI, R1 parallel R2, both are the resistors are connected in series, and we are going to take the voltage across R1 parallel R2. So R1 parallel R2 into, so this is voltage gain, it is output voltage, it is not voltage gain, R1 parallel R2 plus RSI into Vi into R0 parallel RD. So minus Gm. Now I could take this Vi to the denominator. So it is R1 parallel R2, R1 parallel R2 plus RSI into R0 parallel RD. It has already been calculated 4.76K. So Gm, we know it is minus 1.41 into 10 power minus 3. R1 parallel R2, it is 20.6K by 20.6K plus 4K into 4.76K. So gain is, so I will write here after calculating this, voltage gain is, it is negative because there is an inversion in phase. It is minus 5.62. It is the gain of this amplifier, right? So this minus says there will be an inversion between input and output waveform, and with this we would have clearly understood how to solve problem related to MOSFET circuits. Thank you all.